Chapter 12 is titled Relationships Without Boundaries. This is because it's all about the ontological, the physical existence of space-time. If you do much digging around in physics communities, or if you listen to crackpots or just any physicists, especially maybe a decade ago or 2 decades ago, you will have heard them discussing the ether or aether, the existence. It's like the fabric of reality. They all talk about Michelson and Morley and how the experiment should have went this way or this way. Like there's all these different ideas, It's crazy. Well, mainstream physics is just about as crackpottery as claiming that there's an ether. That's pretty much what mainstream physics believes right now. They think that space-time is this fabric, this container, and what Newton thought of. It was like I don't know what. The point is, I think that it just helps them. For some people, they feel the need to visualize reality this way. I don't know why. There's absolutely no reason. The way I view reality is that you have objects, and these objects are basically all part of a singular object. And they're really not objects because they're ever changing. And sure, an object can change over time. That's what's going on. But my point is that they're more, like when you talk about the sun, it's more like an event than an object. Because if you just say the sun, you're talking about the sun today. Or are you talking about the sun yesterday? Or 1 billion years ago? You don't include the 4-dimensional aspect of it. And I know this is deep philosophy here, and it's kind of absurd, but this is the type of stuff that I've done a lot of thinking about. Alfred North Whitehead, if you're familiar with him, he influenced a great deal of my beliefs about reality. It was intuitive for me anyways, because I've always thought this type, like just kind of viewed the world this way. I don't know. I think some people view it differently, but and when I mean an event, it's instead of a noun, it would be a verb. So the sun, it's more like the sun is really just kind of a portion of the universe that is doing something. It's part of the whole. Yeah, so there are no boundaries. That's the idea of relationships without boundaries. The without boundaries parts, we're stripping away the gravitational boundaries. These are human-defined boundaries. When you try to define something like the sun, you have to really pin down exactly what you're talking about and draw these artificial boundaries. So you would say that the radius of the sun is whatever. And that would be where you're claiming the sun ends, and whatever the ether, the space-time, whatever you're claiming happens after that point is not real. Like you're just drawing an artificial radius. Like the sun gradually decreases. In fact, there's no part of space that has zero mass. Like emptiness, nothingness is just the absence of mass. And you don't ever have absolute zero mass. So emptiness is really better thought of as less mass than more mass. And so this is, I know this is insane. This is literally insane talk. But this is how you get here. I mean, this is real. Like this is how you do physics. Because traditionally, physics is done in a way that is like we do this equation and we have these boundaries and these parameters. And then they'll say, with the observer at infinity. That way you're not including any kind of additional problems. You're like setting a constraint on the way you set up your equation. That way it's a factual statement. But in reality, that's not how the universe works. I mean, everything is just part of the whole. And so this impacts the way that physicists think about problems. It influences the directions that they're taking, the ideas that they have about how to solve these complex problems. They view space-time as being curved around mass, and that's what general relativity is. But curvature is just this word that we use to describe the way the math works out. Curvature is really, it's not what is happening. It's just that gravity tells other mass what to do. It's not telling space-time what to do. It's actually telling mass what to do. Mass and energy. It's telling them what to do. There's no space-time there. And the reason that the space-time, like, sure, you can say that it's curved and you can use it as this abstract word, just like we define Earth. It's very useful to think of things, to use these abstractions, like Earth is this idea that it's this planet and that we live on it and we can give it a name. But if you zoom out, when I mean zoom out, I don't mean just spatially, temporally. Earth is just, it's a brief existence over the course of 10 billion years. It's just this blip. It's a planet formed, and then who knows what happens. It gets destroyed by an asteroid 15 billion years after its creation. And then 100 billion years passes, and when you talk about Earth, it's like, what do you mean Earth? Like, these boundaries are just, they're fake. And there's no gravitational boundary. It depends on, like, it's all, like, whatever metric you want to draw, but it's observer dependent is really the most fundamental. It depends on, and observer dependent doesn't mean you have to have a conscious observer. It could just be whatever's absorbing the radiation. So I had to pause it for a second. I am sitting on my porch. It is mid-October. It's an amazing night. There's tree frogs. That's about the only thing you hear. Now, I have heard a couple katydids try to muster a call, but they've gotten hit with a chill. So, I mean, it hasn't been too cold, but right now it's probably 60 degrees, which is quite cold for a katydid, I would expect. Tonight would be the first night that they have not been extremely loud. But I was sitting here. I'm in Western North Carolina. This is close to my birthplace. And I love these rednecks. Don't get me wrong. I love them. I am one of these rednecks. These people are my people. But man, when they are young, they sure know how to raise hell. So probably 20 minutes ago, I had to pause it because somebody was driving down the road, the road is a good half a mile from me. Or a mile even. It's not a mile, but it's a long ways. And there's trees, like I'm in the middle of the woods. This guy drives by and it's the loudest vehicle you've ever heard. Like, it is just so obnoxiously loud. And as he's driving by, every dog ever, like dogs I didn't even know existed, were barking. And they have not stopped. Like there's still dogs in the distance barking, but I just now stopped hearing it. Like it sounded like he was driving at 3 miles per hour, but it was the loudest, like he was just accelerating the engine and it was just not moving. I don't know what was going on. I was like, what is going on? Is he just doing donuts there? And it was just slowly moving away. It's the craziest thing I've ever seen. Anyways, I wanted to share a story because this is, I wanted to give you a taste of how amazing I am. I'm such a boring dude, man, complaining about some kid down there revving his engine. But it was such a peaceful night, and he ruined 30 minutes of it. I was on a roll, and I don't even know what we were talking about. We were talking about the ontological existence of space-time in Chapter 12, Relationships Without Boundaries. So the idea is that mainstream physicists believe space-time is a physically real thing. And they think that general relativity is what forces this upon them. And they're wrong. General relativity is about relationships. It's about relativity. It's about relationships between mass and energy. Not space-time versus mass and energy. Space-time doesn't even have to be a part of general relativity. You could actually formulate general relativity without space-time. Just do it with all about relationships. There's no need to do that. You just have to remember that space-time is not a real thing. The reason it's important is because believing it's a real thing actually violates general relativity. The whole argument. Look it up. You can read for the next 6 weeks about the whole argument. I'm telling you, there is all kinds of good material of people debating the whole argument. You'll have to dig pretty deep for it, but if you just Google it, I think Stanford has an amazing, amazing article. Like, I mean, it's a 3 days worth of reading. That'll give you a good introduction, and then you can buy a book. But you don't have to do that. You just have to understand that space-time just means the vacuum, which means the absence of mass and energy, which just means less mass and energy. That's what it means. It means less mass and energy. When you're talking about outer space, when an astronaut goes to outer space, he's going to a place of less mass and energy. He's going to He's moving through the gradient of mass and energy. There is no place in the universe where there is no mass and energy. There's no true vacuum. This is synonymous with saying space-time does not exist. That space-time is not a physically real thing. These two are synonymous. They mean different things. To say space-time is not physically real, and to say there is no true vacuum. Those are two different statements, but they mean the same thing. And they both prove that the universe is not expanding. And you can do this through a series of postulates, but the FLRW metric requires there to be some equal expansion. It's a uniform expansion of the space-time metric. And so it's what that really equates to in the real terms and back in the real world is that you're saying that like you're giving a repulsive energy that overcomes the impacts of gravity. And so there's no way to do this. There's no way to do this even if you have some unknown energy source. If you're just going to try to describe some new phenomenon like the electromagnetic force is different than gravity, if we're just going to add another fundamental force to this and you're just going to call it dark energy, it doesn't work because you're canceling gravity out. So that's why their shit doesn't work. Sorry for my language, but I don't know what else to say. This is like, there's no reason. The problem is that I have no one to talk to, no one to debate. They just immediately reject papers. So I'm on YouTube and it's the most boring nonsense ever. And so the average person listens to this and they're like, this guy is retarded. And the physicists even listen to this and this guy's retarded. Like this doesn't make sense to them. But like, I need to know, like, if I could have just a conversation with someone, they don't even answer emails is what's crazy. I guess I've kind of stopped even trying. I gave up a while ago because you just sound like a crazy person. But it's just this one simple thing. If you just get rid of the ontological existence of space-time, and you have to also get rid of the idea of homogeneity. But the idea here is that space-time is not physically real, so you can't assign properties to it. You can't say that it has some repulsive energy that makes mass expand, because then you're violating diffeomorphism invariance, which is the basic foundation of general relativity. The whole argument. Read about the whole argument. Like, I don't know how, like, the whole argument is settled. The whole argument invalidates lambda CDM. It invalidates dark energy. You're not going to do it with back reaction. That doesn't even make sense. I'm sorry. You just have to have a scale-dependent mass density. You can't assign homogeneity. You can't assign the same mass density to all points of spacetime, because spacetime is not what contains mass density. Mass density is scale-dependent. We have mass and energy, and mass density is scale-dependent. So the largest scales have the smallest mass density. You can go beyond the observable radius. You can think about the universe as 100 trillion cubic, whatever, cubic light years, or a radius of 100 trillion, like just the biggest volume of space that you can think of. The mass density of that will not be zero, and it will not be the same as at the observable radius. It will be much, much less, but it approaches zero. The further out you go. At infinity, it is zero. But you don't have to worry about infinity. We don't have to worry about infinity because we have the Schwarzschild limit. There's a horizon. There's an observable limit because as light transverses this medium, it is gravitationally redshifted. Unless it's Hawking radiation. If it's Hawking radiation emitted from the quantum field, then it's the opposite of the metric. And it's the observer's in the center now. It's the same metric, though. It's just this is actually the conservation of energy. You have two different perspectives, one side and the other. And so from the quantum field's perspective at the horizon, it's a blue shift. Regardless, the geometry is the same. It's the geometry of the mass energy, though. That's what we're talking about. We're not talking about the geometry of space-time. We're talking about the geometry of the mass energy of the universe. at the observable limit. So you don't have to worry about infinities. There's an upper boundary and there's a lower boundary. That lower scale is the emission of the CMB temperature. Why is it the lowest? Because Hawking radiation decreases with the radius. The temperature of the Hawking radiation decreases with radius, and black holes are already emitting basically there's nothing smaller energy scale than Hawking radiation. I mean, it is very tiny, especially when you get to massive black holes. And when you're talking about a coordinate singularity, the size of the observable, or the size of the observable limit, or the Hubble limit, then the emitted Hawking radiation is very, very cold. I mean, we're talking I think it's 1.4 times 10 to the negative 30 Kelvin. And so this is the lowest energy scale. And this happens at 2 Planck lengths from the horizon. I've got some equations here on the screen. This is for a new Planck length. This is just a way to derive this lower energy scale with a simple equation. And it's, quite intuitive. So what this is you can take the temperature of the Hawking radiation emitted squared divided by the observed temperature squared. And so this accounts for the full geometry. And then you multiply that by the horizon radius. And that is approximately 2 times the standard Planck length. Why is it 2 times? I don't know. Shell. It's because of the holographic principle. You're talking about the shell of a sphere. That's what I think. If you want to know that, so that's what you have to have. So you divide that. 1 Planck length would be the width of the shell. The reason that it's 2 Planck length is because the shell is present at the emission location and at the observation location, absorption. And so that's why you have 2 Planck lengths. It's because it's including those 2 Planck lengths. You have to have a minimum length scale, and so the minimum length scale would actually be the width of the shell. And what I mean by the holographic principle, well, look it up. I think if you've listened to the book, you should have already had me. I should have already talked about the holographic principle. I don't have to cover everything. This is just chapter 12. How far are we? Oh, we are 23 minutes. That's great. I wanted to talk for a while on this one. This was my favorite chapter. This is the most important. Man, we made it through this. I can't believe it. I struggle. I don't do stuff like this. I was a C student. I don't do homework. I really liked researching physics. I've spent the last 15 years reading books and I have whiteboards. I would do physics, man. I would do it. I did all kinds of crazy, stupid shit. But it was fun. The research part was so fun to me. I was super obsessed. And now that I have to tell everybody about it, it's like, man, this is so much like work. This is so difficult. I don't like talking into a microphone. I can't believe I wrote a book. I used ChatGPT to help me write it though. Let's be real. It's obvious in it, but I wrote it all the way through, and then it made corrections and I would have to argue with it, and that took forever. I mean, it was like I was paying $200 a month too. I was paying for the strongest model because this shit's complicated. But now I really like going back to 4.0. It's so much cleaner at the equations. The new one, it just overcomplicates everything, and it just makes all these crazy assumptions. that don't even make sense. But it's, it's good. Don't get me wrong. But they're, man, you have to hold their hands, especially when you're doing shit like this, because they're like, no, that's not right. And I'm like, no, you're not understanding me. You have to, and then sometimes you just have to ignore what it says, like, and then delete everything that any corrections it made. Like, I found that Grammarly was so much better. I don't like to use the AI in Grammarly, but just like I would put my stuff in ChatGPT and it would change it really dramatically. And I'm like, no. Like, I really just wanted it for helping with spotting bad words and phrasing some of the language. And, I kind of wanted to make it a little more technical than what I like to write. And I definitely needed help with the LaTeX. It's just the code. Like, I don't know that shit. And so I used TextWork or Text Studio, which is that's my favorite. Like, I've used all kinds of things. I've used Scrivener. That's what I wrote my first book with, Scrivener. And that was in 2016 when I was writing that. And that took a full year. And it was short. And it was kind of pathetic. Like, it was terrible. Like, I screwed up a lot. Like, I don't even want to go back and look at it. Like, I cringe when I think about it. But this book, like, I'm a little more proud of it, but it's really super short. And as I read through it, I'm like, wow, I should have expanded on this. I was in a rush, though. And like I say, all I cared about was chapters 1, 2, 3, and 4, which is basically just the cosmological principle with Einstein's universe and mass density, scale dependent, and homogeneity, all of that stuff. And then the CMB temperature, that one right there was really important to me. And then all the rest of the shit I didn't care about. Like, I don't care about BAO. That is such a nonsensical thing. I don't know what it means. It's so complicated. But I mean, I have it. Like, this makes sense. Like, I don't know what it means, but it's like at the horizon, you can use the Tolman temperature to do exactly what they do. So I don't know. Like, this works. Like, I can get the BAO scale. Like, it's pretty simple. So I understand it that far. I just don't know what they're talking about. Like, is this really matter creation? It may be. I don't know. But that stuff is kind of fun to think about it. But I get confused a lot of times with mainstream physics because they really super overcomplicate things for no reason. Absolutely no reason. First of all, special relativity and Newtonian physics are amazing. Those are the funnest because you can wrap your head around it. General relativity, once you've wrapped your head around special relativity, general relativity is kind of cool too. Like, it's a struggle, but you don't have to do all the super hard equations. You just have to understand how the Einstein field equations balance out, and then all the different types of metrics that people have created, the different types of solutions that have been found. That's what I did. Like, you don't have to really do a bunch of crazy equations. You just have to make sure you have a balanced set of field equations, and that's kind of easy to do, especially with ChatGPT. It'll be like yes or no. Like, it'll tell you for sure and it'll help you too with that. Now, it's, like, you have to hold its hand, so you have to know you need some good books in your lap while doing it, and you need to be able to grind, and I like that. I like doing that. That's fun. I like figuring out that stuff, even though I don't know math. I'm terrible at math, but really, like, I know I'm good. I can get I could ace algebra 2 right now. I could make an A+ in algebra 2, and I failed that in high school. I had to retake that. It was hard for me, but I could ace that now. So that's where I'm at now. I don't know about calculus. I'd probably get a D in calculus. But you don't need to know it. You don't have to do this. Like, you don't have to do a lot of crazy. Physics is different. Physics is about parameters and about constants and variables and about simple algebra. I mean, you can get as crazy as you want and as detailed and specific of situation, but That's not how you communicate in physics. You want to simplify it to the best scenario possible. And so you got a little bit of philosophy involved in there. And so I enjoyed that, figuring out like exactly why they are so hell bent on an expanding paradigm. And it's honestly, it's because I think that there's hopes. First of all, they've not heard this perspective. As far as they know, Einstein was like, yeah, if you don't have an expanding universe, then it collapses. It just collapses. And so that's what they think. And that's because they're using this homogeneous cosmological principle, because this was also Einstein. So they're just standing on his shoulders and they're not really thinking about it. Like there's a few, like Burchard, who's like, there's quite a few, especially most recently, that have been talking about the cosmological principle and redefining it. And so there is hope there. Especially I'm putting it out there, like this works. So if you just share this with some professor, they can email me. Like I never get emails. I would be more than happy to discuss this with anyone. Like what I'm claiming here is very simple. It's a very simple thing. You can't use homogeneity. You have to use a density profile. And what I mean by that is, take a look on the screen. I built this visualization. It means that any radius, you just choose any radius and any starting point. Any starting point with any radius from 0 to infinity. What profile do you use? How did your density evolve over the course of that radius? So if you choose, let's say 13 billion light years is the size of your radius, how much mass is in that radius, in that volume? And what is your density? And then half of that, now go to half of 13 billion, 6.5 billion. Go to 6.5 billion light years. How much mass is in that volume? And then now do half of that. How much mass is in that volume? And so that's what I'm saying. You can't use homogeneity. You have to use a scale-dependent mass density profile is what I call it. It's just, how does it evolve along R? How does it change? And it has to be scale-dependent. And so this means that it's changing smoothly as you go along R. And so whatever profile you want to give me is going to have a distance proportional gravitational redshift. Unless you say it's homogeneity. If it's homogeneous, then you beat me, you win. But it's not real. Then you'll claim that it's statistically homogeneous. No, that's not. They'll say it's homogeneous on the largest scales. No, that's not real either. And so any other profile that you give me is going to have a distance proportional gravitational redshift, which means at least, at the very minimum, it's a portion of Hubble's law, or the Hubble redshift, is gravitational redshift. At the very least, because that is not accounted for in mainstream cosmology, a distance proportional gravitational redshift. That is unaccounted for. And so, if you account for it, if you just assume that it's all created by gravitational redshift, it's a 1/r profile, which also happens to be the only profile that is isotropic. I'm sure that there are others that you can create, but it's the simplest. And 1/r squared doesn't work. 1/r squared is this, you end up with objects that aren't stars and galaxies on the larger scales. It's not, the largest scales will be not made of different objects. Like, it doesn't work. Same with 1/r cubed. These profiles do not work. But 1/r works. And it's stable. And it produces a Schwarzschild horizon that produces Hawking radiation. And at that horizon, you have the exact geometry needed at 2 Planck lengths from the horizon. You have the exact geometry needed to produce the 2.725 Kelvin in the CMB. And so we have 2 length scales there, which makes, and also if you just include that the vacuum energy density is just this idea, it's not real, because this is all coming from everything that I've said so far is based on the idea that space-time ain't real. And so how can space-time have some energy to it? So there is no cosmological constant. The cosmological constant is just this mathematical idea of the way that it balances. It's just the distribution. It's just basically the structure from another angle, from another perspective. It's nothing, because space-time doesn't have properties. I'm starting to get a little rambly here. Oh, so this also at the Schwarzschild limit, where we have this upper and lower boundary to gravity and the energy scales and length and all this amazing things that we can do with this, we also have a uniform gravitational acceleration. And the surface density of this shell that I mentioned earlier is 2 times the coupling constant K, which is, this is how the profile works through. It's just the most amazing thing ever. Like, all of these variables tie in together. And so if you adjust one, everything changes. And so it's very easy to fine tune. And it's around 72 kilometers per second per megaparsec. Something like that. Like, do we make this shell at 2 Planck lengths? I don't know. Like, there's a little bit of fine tuning there to discuss. Like, I guess it would be. Like, you would just make it so it ends up being something like 71,000 something meters per second squared per megaparsec. So there's, there's a little bit of adjustment, but we also have this uniform gravitational acceleration. I want to get back to that. Uniform gravitational acceleration is also dark energy. This is why, gravity perfectly mimics dark energy. But this gravitational acceleration also gives us rising curves in dark matter, in galaxies. So there's no need for dark matter, because now we have rising curves. So really, we have too much mass. Now we have too much mass. The reason we have too much mass is because our profile assumes that there's no breaks. But you can plot it. In the book, there's plotted. I created images where I plotted all the realistic objects. So you can plot galaxies along a line, and it ends up being around 1 over r. Like, you can plot them perfectly on the 1 over r line, along with stars and atoms and protons. Like, everything lines up for 1 over r, which is Hubble's law, as gravitational redshift, not as expansion of space. So I'm convinced that the universe is not expanding. There's no way anybody will ever be able to convince me of any other, because this makes perfect sense. We have no more mysteries. We've solved basically all problems. Not all problems. We want superconductors, and there's a lot of major problems. But these are all the major problems. Like, this means that general relativity is completely compatible with quantum field theory. It doesn't result in infinities, because the vacuum energy density is this relative phenomenon. It's a scale dependent. It's just mass density is just another way of talking about the mass energy density of the universe. It's just it's not a repulsive force. We don't need it. What else? Oh, the BAO nonsense. I mean, that works out perfectly. I don't know. All from saying that space-time is not real. That it's not even. You don't even have to say that. Like you can just say there is no true vacuum, and all of this comes out of that. Because the reason there is no true vacuum is the exact same reason you can't use homogeneity. The universe is not expanding. Thank you for listening. Subscribe. Give me a thumbs up. Buy the book. You owe me $5. Right now, you owe me $5. If you buy it in the future when I change the price, if I change it to $52 next week because for whatever reason, because I need money and I'm selling books, then now you owe me $52. So you better buy it right now while it's $5. I'll probably change it. I don't know when I'll change it. I think I'm probably breaking terms of service of Amazon right now by telling people that I will change the price. But this is just an introductory price that I will leave for an introductory period of time, and that is all I can say right now. It may be a year. Like I'm not crazy, but you owe me $5 at least. If next year, if it's 2026 and you're listening to this, you owe me whatever the price is in 2026. I love you. Have a good night. Bye-bye.